channel attacks. Let's see what a side channel attack first, then get into what I'm doing. So this is a device. So it's a Raspberry Pi, and so when this works, let's say it's calculating some, it's running some cryptographic code there that involves plain text and a key, and it outputs some ciphertext. So ciphertext is the output of the cipher. So the cipher is the encryption algorithm that's running on here. So okay, so while this code is running inside of this device, we can listen to the effects that this device produces. So that by effects, that I mean when this device is working, it interacts with its environment. So sound is one thing. So when the CPU is working, some CPUs, depending on their power draw, they induce a coil whine. So if you have any power units that have coils in them, so there's a little bit of coil whine. So if you have PC at home, you would hear some things when the load is high. So that's one way. So electromagnetic emanations is another way. So we can measure the delays in remotely that happens through the network, and we can also measure power directly by hooking into the power supply of the CPU. So what we do is we collect these traces and analyze them and arrive at the key using this data. So this is a quite involved method. This is just a brief overview of how we do it. I'll explain it later, but this is the main idea here. So because an device interacts with when it works, it's whatever the secret stuff that goes on in the device, it can leak due to this effects that when it interacts with the environment. So what's my goal? So my goal is to start with a leaky implementation. So the leaky implementation here is the encryption algorithm that's running on the device, and do something that's automated without, let's say, least amount of manual work, and come out with a leak reduced implementation. So I produce some software implementation of the encryption algorithm that is less leaky. So what we target here is to automate the process of this. So there has been past research that have done this manually. So there's a whole lot of technical, very expert. There's a lot of expertise around this area on how to do it manually, but there's a very low amount of, or next to none, automated ways to do this. So let's see how this leakage happens in a device. So the cause is actually, we can if we magnify into the causes that are causing the leakage, we can drop down into a register. So let's think of a register as a set of bits that are depicted here by a set of light bulbs. So this is a 8-bit register. So in an 8-bit register, all lights are up. So that means all bits are set to 1. So this is the maximum amount of power draw that this register is going to get. Okay, so let's say this is the lowest amount of power draw that this register is going to use, and in between these two levels, there are other levels that are, so let's say we have two bits set here, so another 2 bits. So this is the same power level, the draw as we would see from the outside of the device. So again, another 2 bits, so there's no change in the power draw. So let's draw a graph of as the x-axis, we take the value of the register and the power consumption. So here you see that as the value increases, there's this pattern of power consumption arriving. So here in the red red dot shows that the when the register is filled with all bits, so you can say that that's 255, and when the register is filled with 7 bits as 1 and only one bit as 0, there are multiple matches. So we can say we can have an idea about what the actual value inside of the register is. But ideally, we don't want this. So our target should be to reduce this effect. We don't want this to be happening. We want this to be happening. So if we see that the power consumption is not dependent on the value of R, then we can't say anything about the value of R. So that's what we are trying to achieve. So masking is a way that we can achieve that. So in masking, what we do is we formulate. So we have first a value. This is the value that we were talking about earlier. So we are going to use some intermediate value in this register, and we are so that's related to our calculation. So we are going to formulate it with another value that we keep secret and keep changing. But the importance is that this value is not part of the calculation, but it's distributed uniformly each time we use it. So with this formulation, we come up with another value that the result is uniformly distributed, because a part of this, because we started with a uniform distribution and we don't know what the actual value is after this change. So if we take the original value as the key or part of the key that the encryption is using, we are breaking the dependence of the value that we are observing from the device that's the connection between that and the connection with the true value. So I have referred to it as the key. So it can be a key or part of the key or anything that reveals the secret here. So the next problem is that so we have arrived with something that can secure this device, but is that sufficient? It is not sufficient actually. So let's see why that happens. So let's say we do the thing that I explained earlier to some value a, and we come up with a dash, and we store this into the RAM by using the memory bus. So after some time, we are going to store another value that's again must be the same value, and we are going through the same memory bus. So this happens. So what this is that inside of the memory bus or inside of the device where we write both of these values, they interact, the past value and the current value. So because of this interaction, the XO in the middle of this A dash and B dash is because from the switching between two states. It's switching from one state to another, and that causes the masked value to get removed. So we are again leaking according to our original values A and B. So we can't use new masked values for each time we are doing a calculation. That's not practical. We would have to use the same mask, and this is going to leak. So let us briefly think about what's the actual problem here and how we are going to fix that. So the actual problem here is that we are breaking an assumption. So the assumption is that each instruction in a program is executed independently of other instructions. So each mask value, by definition, each mask value should be independent of other mask values. So that we are breaking that here. So, but we can't help it because this is how the real world works. So this is an actual thing that happens in the real world, but in the theoretic world, we don't find this because we have this assumption. So let's measure. Let's see how to measure this and how to find a leak in a real world using a real device. So so this is the block diagram of the experiment. So we are going to insert a shunt resistor into the power wire into this processor. So like this, and we are going to measure it using an oscilloscope, and we are going to record some traces while the algorithm is run. And so this is my setup at the time. So we are using a discovery board, and we are using a differential probe because we need the differential voltage between the pins of the resistor. So I don't think if you can see that there's a little resistor fitted in between the power rails of the CPU here. So there's a little bit of damage we need to do into the circuit board to do this, but for cheap boards it's not much of a deal. So there are ways to measure things in a non-invasive way too, but we have opted to do this way. So this is how we are going to measure if measure. It's not actually measuring. It's how we are going to see if there is a leakage in our algorithm. So this is a statistical measure. So the statistical measure depends on two sets of distributions. One is the trace samples that we take while the device is running a fixed input. So the fixed input is we are using the same input to the device and make and collect traces while it runs the same input. And we again give random inputs, multiple random inputs, same number as we did in test A, and then collect the traces for the random input. So the difference between these two distributions is going to give us the leakage points, because here what it means that for each sample, if some value, that's it's some power value, voltage value differs according to the random input and compared with the fixed input, that means that something is differing according to the random input that we have supplied. So it's input dependent. So input dependent algorithms are not good as encryption algorithms. So that's why this is connected to security most of the time. So if it's input dependent, there's a more chance that we can get the secrets out of this algorithm. So by the way, this method doesn't guarantee that we can exploit any leakage that we can find. So there's some other leakage limitations here too. I'll get them in the next slide. So this is the graph that we can draw using the results that we get from TVLA. So each point that is more that crosses the significant level. So the significant level is 4.5 here according to the p-values. So we need to get, so we can adjust it according to our significance for the p-value. So this is the t value. So this is from the t-test. So it's a statistical measure of how significant the leakage is. So let us see some limitations of TVLA, because we need to be sure of what we are doing is correct, and we don't want to have a false sense of security by looking at the results of TVLA. So the first one is that TVLA is not an exhaustive security measure. It doesn't mean that if you use some set of fixed inputs and you didn't see any leakages in the TVLA test, if you don't see any leakage, that doesn't mean that your system is secure. So it's dependent on the different number of fixed input that you're using, and there can be some fixed input that that can leakage, that can show leakage in the same device, the same experiment. And the number of trace count is significant to the leakage too. So if you have a very low trace count, the differences might not be that significant, so you won't see that. So if you do a higher trace count, then you would start to see the leakage. And leakage is not always exploitable. So I explained that earlier too. So it's because we only use random input, and we don't know what's the connection to the leakage from the input is. So so there are other attacks. They're actually attacks because you want to attack the secure device and take out the secrets. So this is a statistical measure of leakage. So it is not exploitable. So not every point is exploitable, but some points could be exploitable depending on other attacks. Okay, so let's us see, if we do this process manually, what are the things that we need to do. Okay, so we start out with the startup implementation, and then we run it on the experiment device and gather traces and do the changes that are needed to fix the leakage and repeat the cycle. So this is bad. This is very tedious. This is very involved and takes a lot of time, and it takes a lot of expert knowledge to do this. So in automatic countermeasures, we start with a masked implementation because we know how to automatically mask it. So when we use a masked implementation, we are leaving the masking to some automated procedure, and then we use some leakage detection method and do some code synthesis to fix those leakages, and then the candidate program is run again and again through this leakage detection. So leakage detection can be done in any way, like emulation or something similar to that. And the code synthesis can be done in multiple ways. You can rewrite the code in anything that you have from some library of replacements, or you can synthesize things on the go, but the functionality of the code should remain the same. So we then arrive at a reduced leakage implementation, and that's when we are done. So we have to have some switch in the leakage detection to show that this is enough. So that amount of work is done, and the significance of the leakage is enough to our thresholds, and then we deem the implementation as secure. So let's see what are my contributions in this area. So ours is an automatic countermeasure, and we follow the same recipe. So we use a masked implementation, and as you can see, the masked implementation already leaks. So this is an algorithm called sudo. It's an encryption algorithm, and the masked implementation is leaky because of the reasons that I explained earlier. So we run it through our leakage detection, which uses simulation here. And this the simulator that we use is called Elmo, and we changed that to properly, so that the first version of Elmo, the original version, did not include state-related leakages that, like what I explained earlier regarding to the memory bus. So we added those and a whole lot of other state-related leakages that are seen in the real life. So, and we introduce another rule-based code rewriting code rewriting system called Rosita, which takes the output of Elmo and it replaces the code in the implementation so that it never changes the functionality of the code. It only replaces code that it finds as leaky to be non-leaky ones. So when we run this again and again, and when it goes below our threshold that is computed by the simulation, we deem it as a reduced leakage version. But mind you, there can be some leakages that are not present, that are not caught through the model here, but in this case, we got to remove all of the leakage from the to take it down to low significance. So let's take a look at the changes that I did to Elmo's power emulation model. So Elmo works like any other virtual machine. So it runs code in the virtual machine, and the power model is based on instruction triplet. So it takes only 3 instructions at a time and then calculates the power model for the middle instruction. So what it does is it actually emulates the power to the power that's used by the middle instruction depending on the instructions surrounding it. So this is how it works. So it goes from the start to the end and emulates the power for the instruction at the middle. So our changes are that if you take 3 instructions, there are instructions that are directly above it that set some states in the device, because they were executed before instruction of the yellow 3 instruction. Okay, so because these instructions have been executed before, some state is there in the device. So we found out there are many types of states there. So that's why I showed it in different colors. So all of these states feed in to the middle instruction, and the middle instruction power emulated power is dependent on all of these instructions. So we added this to the power emulation model, and so this is how our system detects root cause. So this is the power model of Elmo. So we have the differential voltage, that's what the emulation model emulates, and we have a set of variables. So, and we have a set of coefficients that are formulated with the variables. And so what we do is we calculate t values for each variable independently. So before it was like this. Before, you only look at the differential voltage, the t values from the differential voltage, and say that, hey, if this is high significance, then this point leaks. But now what we do is because we find out what the t value is for each variable, we know what the cause of the leakage is to a certain amount. Not that we know the real reason behind it, but we know that what variables change is causing the leakage. So because of this, we can apply the functionally correct code. We can replace better fitted code because of this. So this is how Rosita works. Okay, so let us look at some results briefly. And so this is for AES, and we run 100 different inputs at 10,000 traces. So so as you can see, there's a bit of a performance hit here. So you can see the top graph is a bit shorter than the bottom graph. So the actual slowdown is 1.36. So it's about 36% slower, but it is more secure. And for sudo, it's the same setup, 100 different inputs and 10,000 traces. And here we see that there's two more traces that are two more samples that are leaky. So these are not included in the model. So that's why I explained this. I told about this earlier, that our model is not the same as the physical model. I mean, it's what we are trying to emulate, but it's not up to that level anyway. Any model is an approximation. So because of this, we are still finding out the reasons behind these leakages, and we are trying to incorporate them too. So it's about 26% lag here. So yeah, so the next steps. So what I think that's important to do next is that we need to fix the missing leakage first, and we need to make sure that our models are intelligent enough to find new leakages. So this is so I've been working only with a certain type of device, right? So this model is correct for that device and maybe for many other devices, but there can be other devices that have something that we haven't thought of. So it's much better if we have a dynamic model that can learn these behaviors. I'm not suggesting we should go for a machine learning approach, because in a machine learning approach, we don't know the real causes of leakage, so we can't fix it. But something in the middle, such that we can do some similar experiments to build the model iteratively. And replacement code synthesis need to change too, because we still use a library of patterns. So that's not an optimal solution for this. That's why we are getting slowdowns of 36%, 26%, and so on. So we can drop that down. So that's an interesting area to research in. And yeah, and also we need some ways to adapt to multiple architectures. So it's kind of now the replacement are binded to this specific architecture. So if it's better if we can port the ideas into different architectures, and generalizing the limitations of code synthesis is much more related to the point where, let's say, if we have an unknown device, we need to find out if for a given set of instructions in this device, that we can fix each leakage that we can find. So that's a hard question to answer. So given a device, you can't answer that. What kind of a guarantee can you give to the implementer so that this any leakage from this device can be fixed? It's a very hard question to answer. It sometimes could be. It depends on the implementation too. So that's an interesting way. And of course, there is some performance optimization in the way too. So in our newest iteration of the paper, we have gone a little bit into the generalization of limitations in code synthesis, but all other areas remain still open. So let's look at the summary. And we first started with what an side channel attack is, and we explained how it leaks. And we said that masking is not working correctly because of practical reasons, and we showed how Rosetta works, and then evaluated our results using real experiments, and we proposed next steps to improve Rosetta. So that concludes my presentation. So thanks for coming to participating in this presentation. Thanks.
Excellent. Thanks very much, Madura. Questions from the audience, or well, from anyone, of course. Just if you want to ask something, don't forget to unmute yourself first. There's no need to be shy, or you can type something. Viran asked something. Does reducing signal magnitude also reduce exploitability?
Let me get back to
the chat window.
Sorry. How can I go back to the chat window?
Maybe you have multiple windows. Yeah.
Oops. No. No. Maybe I should stop this. Sorry.
No problem.
Okay. I got it. The specific signal magnitude also reduce exploitability. Yes, of course. Signal magnitude is yes. So you can reduce signal magnitude by adding noise. That works, but the issue is that you are going to add signal. So you are going to reduce the signal magnitude by if we are going to add noise. You need to add some hardware device that's going to add some noise. So with that kind of an approach is that you can always bypass that device that adds noise into some trace where you can get a line that has no noise at all, or a significantly low amount of noise. So they have always tried to, like in this example, in the hardware device that I used, I removed the links to capacitors because capacitors usually filter out certain frequencies. So it's always there. So it's best if you can take this noise generation inside of the die. So that's a hard problem to solve. So it's not that practical to have a noise generator inside of the die, and it can interact with other things that are going on in the die too. So that's a one way. That's a very hardware specific way of doing this, but we can still do some work in the software area too. So there's been in the latest research, there's been introduction to a certain instruction where when you use that instruction, it resets all the states that are used in the hardware. So that's kind of reducing the signal magnitude also. So that has been proven very effective, but not all hardware has that. So yeah. Any questions? No.
I have to admit, I didn't know that you had, let's say, taken out some of the capacitors. It makes sense now.
Yeah. So it's actually the capacitors are still in the board. I just damaged the tracers in between the. Yeah.
Sure, that's good. And once everything's well, I guess now that the tracers have been damaged, well, you can always repair them and just see what happens. But probably the entire, all the measurements, all the model won't be that accurate, right?
Yeah, but what we assume is that this device is the device that we use for measuring is not the actual device that we are going to attack anyway.
Sure.
So we are just using this for measurement, and maybe think of it like we are building a template that would suit another device that we would attack.
Cool. Let's give everybody a moment. So you've outlined a lot of potential future work. Out of the projects that you have outlined, what do you think could be tackled within a master's project or an honors project? So a 1 year project, 2 semesters at roughly half a week per week.
Yeah, so I think the code synthesis one would be, I don't know, it can go on for a bit more than 1 year, but I think that would be the easiest one to tackle from the list of ones that I listed here. So because so let's say we have these ideas behind the patterns that we use for replacement. So let's say some kind of replacements use resetting of the state. So we have a target where, let's say we have set some memory bus state and we want to reset that, and we're just trying to use any kind of instruction that would reset that state. So we have a source, a random value source, which we use again and again, but that shouldn't affect the usage here. So it's an independent random number, and we use that with another instruction that would reset that state. So this differs from architecture to architecture. So an interesting question is that if someone can make some language or pseudo language that lets us only worry about the things that we are that are related to the leakage. So let's say if something is leaking on the memory bus, we say that we want to reset memory bus and nothing more. And this whatever the system that is being made, it would come out and mold that language into some output where that specific memory bus reset or state reset is done by actual assembly. So that's totally it's a synthesis to different it's like a compiler or pseudo compiler that is taking bits of ideas from Rosetta. So it only says that here I want to reset this instruction, so this instruction is causing this leakage and I want to reset this, and that problem is solved in a very independent way for each architecture. And it's much easier if this is not manual. I mean, the first few iterations would be manual to different architectures, but it would be very beneficial. I think the best contribution would be if that could be learned in some, let's say use some genetic methods or use something like any topics using optimization. I guess that would come that would use different architectures and run some tests on them. And also it would be much better if you can generate the tests also. So no one should give it these tests. It generates the tests itself and tests. So that's the idea behind dynamic modeling also. So the model is being tried and tested by using some kind of learning or optimization method. It tries to generate its own experiments, and it generates its own model. So this is I think it would be interesting to see some contribution in code synthesis, because I think it's much easier than the model one.
This way you'd be aiming at a single button solution. Kind of you hook up the device, you press a button, and after a week it comes back and says, here's the model, and here are all the things that you well, somehow hidden inside. Here are all the transformations, all the magic stuff that will help you secure your code in the future.
Yes. So that part has two specific parts in modeling and code synthesis. So I think the code synthesis one is much easier to tackle. And also there's performance optimization, but I think that would be too small for that kind of a time period. I mean, you can just come up with some kind of other replacement methods or some other code snippets that we can use instead of the ones that I used. So I think that would have some, it would be not novel enough to be published, and I think.
Yeah, by itself, not no, just as part of a bigger system then.
Yes.
Sure. Oh, there's one.
Okay. So what do you mean by an evolving compiler? So you can explain a bit.
Yeah, if you want to, you can unmute yourself and just talk as well. But entirely up to you, depending on the background noise or so, whatever.
Yeah.
This English comes from assembly.
Yeah, but the compiler doesn't have the knowledge that it needs to apply these changes. That's the issue here. Only when you look at the changes in a different light, let's say, so a compiler can, to a certain amount, a compiler can do this using static analysis. So static analysis is only part of the, it only answers the part of the question. It doesn't answer, let's say, most of the question, because static analysis has its own limitations. So you really don't know what the values are until you run it. So the values are important because the values are what's going to leak. So values and interactions between other values in the, so if you have two intermediate values that are leaky, there are some methods of finding out them using static analysis, but you can't be sure that you are going to find out most of them or all of them. And of course, simulation is not going to find all of them either, because you can't exhaustively test all the inputs. But given that we can parallelize and we have a lot of computational power right now and in the past, and given that the static analysis approach takes a lot of human effort to build up, I think it's much more efficient way to do to tackle this problem. So compilers by themselves is not enough, but if we merge Rosetta with a compiler, and so that's how it works right now. So Rosetta takes out the output from the compiler as assembler, as assembler source. Actually, it stops the compiler halfway. It lets the compiler add all the optimization and everything, and then gets the assembler output, and then changes that output. So this gives the implementer a lot of freedom to code anything they want, or maybe if they want to code in assembly also, they can still give that assembler input to Rosetta, and Rosetta would run its system based on that. So it's still connected to the compiler, but we can't still call it an evolving compiler, because it's not part of the compiler. Actually, it's a different method, and it's entirely different. It's running the code. It's not synthesizing the code. It's also running the code. So it's very different. If we had some static analysis method, we can still say yes, it's the compiler. But this is a different one.
Cool. Yeah, please do keep asking questions. Anyone else?
Mm-hmm.
All right. Well, then, wait, there was one URL that I wanted to share with everybody. Give me 1 second. I have to find that again. So just a quick comment for those who are potentially interested in doing a PhD afterwards. There are some deadlines coming up for applications. A lot of information is there on the website. If you're a domestic student, then there are a few more opportunities coming up for international students, especially for domestics. There are, I think there's a 15th of June deadline. For international students, it's the 31st of October deadline. Then for a beginning, for a start next year in January or sometime next semester 1 next year. Yeah, just to let you all know. Ooh. Oh, I don't have any other questions for Madura. I should be somewhat up to date anyway with what you do. Anyone else? Last chance. Well, if you think you want to ask something in the future, just either look him up, MaduraShelton, or post a question on the forums, and I'll then forward the question to him. No question coming up. All right. Then I would say also 2 o'clock. We would have more time. I'm not seeing anyone else who has any questions at the moment. Then I would say, well, Madura, thanks very much for being available today, for putting this together, and for sharing your recent work and outlining a bit what you plan to do in the next few months, and where the research can be going and how important it can be, or how it can contribute to, well, simply making code more secure. Yep, that's it from my side. I will stop the recording in a few seconds. I'll upload this afterwards. And yeah, for you all, keep in mind the assignment 3 has been posted, and keep working towards your second report and the second video for the course. Yeah, that's it from my side. Thank you very much. Thank you, Madura. Thank all the students who have come along today. And yeah, stay healthy. And I'll see you all soon again.
Bye.
Okay, bye-bye.